We are ready for example 3. Start working our way through these related rates problems. Air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon changing at the instant the radius is 30 centimeters? So if you recall, I tend to start with the given. Okay, figure out all I can, and I write it down so it's there and visible what is given. So air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. What is that? Derivative of what? Volume, right? Air is being pumped into something, that's volume. And then my other clue that it's the volume, cubic centimeters, right? So I'm going to say that the derivative of volume with respect to time, dV dt, is 800 cubic centimeters per minute. How fast is the radius of the balloon changing at the instant the radius is 30 centimeters? So what are they asking me to find? Derivative of radius. So, whoops, dr dt when what? When r is 30. Okay? That's what they're asking me to find. Okay. The note. What formula ties this, what formula am I going to use that's going to tie this together? Volume of a sphere, which is what? Is that a great question we don't know the answer to right offhand?
Yes.
Got a guess?
I'm going to say 4 over 3 pi r squared. No, cube.
That's done. That's exactly it. Let's go.
There you go. Okay. Volume of a sphere, 4/3 pi r cubed. Okay. Let's go. And here's my thing. You know, Ethan said square and then he caught himself and changed it to cubed. I know there has to be 3 pieces multiplying together there because it's volume, right? So it's cubed. Now, if there was a radius and a height, like you hear r squared h for a cylinder, that's 3 pieces. But here, my only variable is r, so it's got to be r cubed. Okay, so let's take this and let's differentiate. Derivative of volume we're going to use is dV dt. Derivative of 4/3 pi r cubed. Four pi, right? Because 3 times 4/3. The 3's will cancel, we'll have 4. Keep the pi. R to the second times the derivative of radius with respect to time. Now, I kind of do a double check. I'm provided dV dt. I'm provided r. The only other thing is dr dt, which is what I'm being asked to find, right? So you have an option. You can go ahead and solve this for dr dt and then plug stuff in, or plug stuff in and then solve it. It doesn't really matter. It just, honestly, in my thinking, it just kind of varies from problem to problem. So I've been trying to kind of be consistent and plug stuff in and then solve. But if you see one, you're like, I'd rather just solve it and then plug it in, that's fine too. Yes?
So we're doing the chain rule, right?
Yes.
So where do we get the dr?
Okay, so with related rates, everything is being done with respect to time here. Okay, so instead of like, normally it's just, if this is a volume formula in terms of R, everything's being done in terms of R. So with respect to R. But we've got this third variable that is thrown in here that we don't physically see, so to speak. And so we're always tagging in, that's the rates there. Then that's where the rate will plug into. Okay, so when we talk derivatives here, like dr dt, dv dt, we know the derivative of something is a rate. And so these pieces will always represent our rates. But it's because we're talking with respect to time of everything. So no matter what, when we took the derivative of volume, technically that's 1. And then chain rule says times the derivative of volume with respect to time. When we took the derivative of this r term over here, yes, it was 4 pi r squared, but then times the derivative of radius, or the chain rule, so derivative of radius with respect to time. Okay, does that help a little bit? This is playing catch up, I'm sure, for you. Have you looked at the first notes? No. Okay. I didn't know what,
He's like, I mean, I was going to, but
Yeah, exactly. I get it. Okay. So, if I go ahead and plug in, I know dv dt is 800. 4 pi r, what were we being told to plug r in as? 30 squared. And then times dr dt, which is what we're trying to find. I'm not even sure if I multiplied this all out or if I just went ahead and divided it and then, worked with it. 30 squared is going to be 900 times 4 is going to be 3600. So 3600 pi dr dt. If I solve for dr dt, I'm going to have 800 divided by 3600 pi, if you will. And then there's some canceling that can be done. I'm realizing I left something out in my answer key. My brain says, oh, the zeros cancel because they're hundreds, right? So then I have 8 over 36. 8 and 36 both divide by 4. So 2 over 9 pi. It depends how you leave your answer. A lot of times we'll leave the answer like this because officially we technically never had to pick up a calculator to do this problem. Like this could be a non-calculator problem here. Now, are there some answers that you'll see in decimals as well? Yes. So there's not a specific, if you weren't allowed to calculate this problem, you would stop here and leave your answer this way. If you were allowed a calculator, it would just kind of depend on the situation. What would be my label here? I didn't throw labels in like I did a little bit the other day, but this is a change in radius over time. Radius is measured in centimeters per minute. Okay. And I think I demonstrated with the previous one on Friday how you can put the labels in and kind of cancel them as you go as well, can't you? So I have it here in my notes, but I didn't actually do it here. Okay. Let's talk about a ladder. The top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. Typical calculus problem, guys. Just saying. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? Okay. I'm going to draw a picture with this one, and I haven't been drawing a picture every time. However, in a situation like this, the picture is more necessary. So you have the top of a 25-foot ladder is sliding down a vertical wall. So there's my wall. There's my ladder. It's a 25-foot tall ladder, right? And I'm going to draw the floor, and we should be able to assume that the floor and wall are going to meet at a right angle. You would think that's a good assumption. Okay. And it's not that I had to draw the wall extra long and the floor extra long, but so top of a 25-foot ladder is sliding down a vertical wall. Now, we need variables. And so in order to represent the wall, because this is a vertical element, I'm going to use y. Because I'm also going to need a variable for the floor. And since the floor is a horizontal element, I'm going to use x. Do they have to be like that? No. Pick whatever variables you want. But that's my reasoning for doing what I'm doing. And you'll see that trend in calculus. So, if the wall is represented by y, and the ladder is sliding down the wall at a constant rate of 3 feet per minute, what is that that's changing? It's going to be the change in y. So dy dt is going to be the ladder sliding down the wall at 3 feet per minute. And actually, I could put that in given, I guess, rather than, because my triangle's getting kind of... Okay, so the change in y over time. Now, think about it. It's sliding down a wall. What are your thoughts there?
There's friction. Yeah, that too.
Whoa.
Okay. The calculus teacher was looking for negative. Your physics teacher may be looking for friction. What if we had the calculus?
Friction is not fun and it's not my friend.
It is. I like Christian.
Okay, so top of a 25-foot ladder, sliding down a vertical wall, constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground. So that's saying when the top of the ladder is 7 feet from the ground. So that's saying when y is 7, right? I'm not going to make this side 7 because it's not saying it's always 7. But at the point, it's going to end up over here, when y is 7, what is the rate of change of the distance between the bottom of the ladder and the wall? What are we looking at there? The bottom of the ladder and the wall. So we're wanting to know the rate of change as that ladder slides away from the wall. And so we're being asked to find what? Dx dt. If the floor is x, then we're being asked to find the change in x over time. So we're being asked to find dx dt when y equals 7 feet. Okay. The no. As I said, if I didn't have these, I'd probably, wouldn't even put the no up there. I do the given, here's the information we're given, here's what I'm trying to find, then I pick my equation. What do we know? I need an equation. What equation connects this? Pythagorean theorem. Now, with our Pythagorean theorem, x squared plus y squared equals,
C squared?
I'm not going to use z in this particular case. I'm going to use 25. Because that is a set distance that is not changing. And because it's a set distance not changing, we're not going to have a dz dt information, right? If you think ahead to derivatives, we're not going to have dz dt. Okay, let's differentiate.
Put that in the no part.
Oh, well. Yeah. My brain was like, okay, I'm writing down my equation. I'm ready to differentiate. That's where my brain was going with this. Derivative of x squared. Two x times the derivative of x with respect to t plus derivative of y squared. dy dt, derivative of y with respect to t, equals derivative of 25 squared. 0. Not 2 times 25 times, I don't even know what else you would put there, but 0. Okay. This is one where I feel like I usually solve before I put my information in. I'm not saying you'd have to, but that's what I feel like I usually do here. So I'll demonstrate that here just as an example. What am I trying to solve for? Dx dt. So if I subtract it over, or if I keep 2x dx dt, subtract over the other one, negative 2y dy dt. Then if I divide by 2x to get dx dt by itself, if I divide by 2x, what if I say the 2's cancel? Are you okay with that concept? 2's cancel. I'm going to have negative y divided by x times dy dt. Okay. You ready? Just put up here because I'll know I need a little bit of room. So dx dt equals negative y, negative 7 over x. What's x? Well, we need a number. We're at answer time. We need numbers.
Oh, 24.
No?
That's not 25. That's the 1 minute.
No?
Seven.
Y is 7, right? At this point, it's not 7 the whole time, but at this point, y is 7.
Do you have to do like cosine?
Pythagorean theorem. Could you use cosine?
Like,
well, but we don't need to know the angle. We need to know the other side. So Pythagorean theorem is better for this situation. I'm not saying we couldn't use trig, but so think about it as x squared plus 7 squared equals 25 squared. So x squared is 625 minus 49. X squared is 576. Square root of 576 is 24?
No, sure.
It is, I promise. And so now, there's negative y, so negative 7 over x, 24, times dy dt, which was determined to be negative 3. Negative 7 times negative 3, 21 over 24. Oh, I should have reduced that, huh? 21 over 24, both divide by 3. 7/8. What would dx dt have a label of? Feet per minute. Those are the right labels of the problem, yes. Because it's the rate of change between the bottom of the ladder and the wall.
Is that the answer?
I'm sure there's a decimal equivalency. So,
Oh.
okay. So be aware for that situation where you have to work extra pieces to find something. It happens.
So basically, we're like taking our information and differentiating an equation that we want.
Pretty much. I mean, you find whatever equation that works, that connects everything. You differentiate it, and if done correctly, you have all the information to plug in. If done correctly. Okay? That one we hit a problem, we're like, oh, we're missing a piece of information. But when you go and look, oh, hey, Pythagorean theorem connects this. I can't use it and say that x is always 24, but y is not always 7. But at this particular point in time, that's how those pieces connect, which is what we needed. Okay? Okay, 5. At noon, ship A is 150 kilometers east of ship B. Ship A is sailing west at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Got it? Okay. Let's see. How did I want to set this up? We've got a ship going east and a ship going, sailing north, right? No, sailing west and north. That's what it was. Okay. So at noon, ship A is 150 kilometers east of ship B. I need my compass for a moment. Okay, there we go. So, ship A is 150 kilometers east of ship B. Right? That's at noon. Keep that noon in mind. It will matter, right? Ship A is sailing west at 35 kilometers per hour. So it's going that way at 35 kilometers per hour. Did I use X and Y on this? Kind of. Yeah. Okay. And ship B is doing what? Sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? So we're looking ship A starts here, but its distance is moving, right? Ship B is moving up here. So we're looking at the diagonal and wanting to know how it's changing. Now, similar to the last one, I would use an XY, and then this one, an XY type thing. And this one, we're also going to have to include Z because what is it asking? How fast is the distance changing? So it's wanting to know how fast that is changing, right? So if I call, let's see. Okay, hold that thought on X for a moment. I'll come back to that in a moment. But X being the horizontal, right? This 150 kind of changes things. Vertical is going to be Y, and then my hypotenuse basically is going to be Z, yes? What does that make the 25? 25 kilometers per hour is going to be your dy dt, because it's a change in Y. If we're being asked to look out how far apart, or how fast the distance between the ships is changing, we're being asked to find the change in Z. So we're being asked to find dz dt, right? Now, horizontal we want to label X, right? And it is X, other than we had a set distance of 150 to begin with. that they are 150 apart. And so if I recall correctly, yeah, we want to, instead of just calling this x, because we have that set distance, I'm going to call this side 150 minus the distance of x, because it's 150 to begin with, and then as you get closer and closer and closer, it's taking off that distance of x as this car A moves this way, or excuse me, ship A. Okay, so I'm going to use 150 minus x there. Oh, and 35, I forgot to fill in 35 is going to be your, it is still the change in x, because that's the piece that's changing. So that is my dx dt. And that picture got really busy really quick. So hopefully you're able to keep it neatish. I guess I should have filled in some of it over here. So given, we knew that dy dt was 25 kilometers per hour. Dx dt was 35 kilometers per hour. We're being asked to find dz dt, and I'm going to say at 4 p.m.
So we got here like the DZ, DT, over the line.
Well, I didn't do that just because it's not that we have a value we're putting in 4 for.
Not very
Not exactly. Hold that thought, okay? What's our equation that ties this all together? What's our no? What? Pythagorean theorem. So it is x squared plus y squared equals, this time I'm going to say z squared. But I can use 3 variables this time because I'm given 2 rates of change and asked for a 3rd rate of change. So that should make sense that we are using, 3 variables. Well, okay. My brain automatically said x squared. What are we really using to represent the length of that side, though? The 150 minus x. Okay, so we know it as Pythagorean theorem that relates them, but, and if you want to change that up and no, you can. It's going to be the 150 minus x quantity squared plus y squared equals z squared. Okay. Let's go ahead and differentiate. We can do derivative of 150 minus x 2 different ways. I don't have a preference here. There was a part of me that wanted to FOIL it out and then do the derivative. Nothing wrong with that other than you're going to have multiple x terms and multiple dx dt's, which you have to factor out. It's doable. But this actually isn't bad to just take the derivative right here with the power rule. Something raised to the second is 2 times 150 minus x, right? Subtract 1 from your exponent, so we're at 1. Times the derivative of the inside. What's the derivative of the inside? Negative 1. How do you... Could I just tack that onto the front and make it negative 2, or is that going to be too confusing? Maybe I shouldn't. I probably shouldn't do that. I guess I have negative 1 in my notes, so. Times negative 1. This is all in relation to x, so then times the derivative of x with respect to t. Plus derivative of y squared. 2y dy dt equals derivative of z squared. 2z dz dt. Now, I would you say how would you feel if I said we could divide 2 out of everything here to make this equation a little cleaner? Do you see it? Now, I'm not saying you have to, right? But we've got 1, 2, 3 terms. That one's really big, but they all have a factor of 2. So one option here is that the 2's can all essentially cancel out. If I go ahead and take this -1 times 150 minus x, I could rewrite it as -150 plus x. Because it's an equation, and if I can divide, everything has a factor of 2, so I can divide a 2 out of everything. You don't have to. You could leave the 2 in there and work with it. It's just it's just an extra value. Your numbers end up a little bit bigger, but you could work with it. Plus y dy dt equals z dz dt. Now, okay, take a moment and look. We have dy dt and dx dt in our given, right? We know we're trying to find dz dt. What is the information we don't have that we know right now, or we haven't figured out? We don't have values for x, y, and z, do we? Okay. Which is where this problem gets a little more complicated than what it looks. I'll be honest, I started doing this problem, I thought, oh, piece of cake. There's a little twist here, because we need to know x, y, and z. X, y, and z are the distances when at 4 p.m. So think about this. Okay? If we talk about ship A, what do we know about ship A? Actually, I don't want to say equals there, but ship A, first of all, it's traveling the distance of x, right? So we're going to think x here. But what do we know about ship A? It's traveling at a rate of 35 kilometers per hour. How many hours are we talking about? The problem started at noon. We're being asked at 4 p.m. So this could be 35 times 4 is how far ship A will have traveled. And 35 times 4 is 140. And that would be 140 kilometers. So that's ship A, which is the distance for x. We also need to know y, which is going to be ship B. Ship B is traveling 25 kilometers per hour. Over the course of 4 hours, 25 times 4 is 100. So ship B, or the y distance, is going to be 100. What do we still need? Huh? We need z, don't we? I'm not sure I'm leaving myself enough room. Okay. We need z. Z is we don't have a rate or anything there. That's what we're trying to find. So z is the hypotenuse of a right triangle. So z, we're going to use our Pythagorean theorem here to find z.
For A, do we have to do the 150 minus?
No, because x still represents just how far the ship has traveled. Okay. Now, the 150 minus x will apply here into Pythagorean theorem. But in terms of x, that is just how far ship A has traveled. So if I have 150 minus x quantity squared plus y squared equals z squared, plug in your values we just found. 150 minus x is going to be 140. So 150 minus 140, quantity squared, plus y squared, which is 100 squared, equals z squared. $150 minus 140 is 10. 10 squared is 100. 100 squared is 10,000 equals z squared. So z squared is 10,100. So z is the square root of 1,100 if you ask me, or 10,100. I left it as that because I have a decimal answer. Here's my final answer. I will say I know when I checked against the answer key, there's a double zero here at the end, and so the square root of 100 would be 10. So I know the answers key said 10 square root of 101 on this. It's whatever, okay? They're equivalent. Okay. I think we're ready to go back here and fill stuff in. I think. We'll find out. Negative 150 plus x. What is x? 140 times dx dt, 35. Plus y. 100 times dy dt, 25, equals z. Square root of 10,100 times dz dt. I know negative 150 plus 140 is negative 10 times 35. It's going to be negative 350. 100 times 25 is going to be 2,500. Square root of 10,100 times dz dt. Let's see. Negative 350 plus 2,500 is going to be 2,150. Let's see. And if that's 2,150, and then what am I going to have to do? I'm going to have to divide by the radical. Is that making sense there? So I'm going to say that dz dt is 2,150 divided by the square root of 10,100. That is the change in z over time. So my label would be kilometers per hours. And officially this would be at 4 p.m.
We can like
What?
we can leave the square root in the denominator.
Debatable. I was just getting ready to say, or 21.393. I see a nod. Someone's checked me here, so 21.393 kilometers per hour is your decimal notation. Honestly, in a multiple choice, you guys know you have to make it match, right? You leave it whatever form they need you to leave it in because you're looking for the multiple choice. And open-ended, honestly, I don't think they, a radical in the denominator I don't think would be counted wrong. Okay? Because it's equivalent to the right answer. Okay. That's a little more challenging.
Yep.
Can we at least get through 2 more and just not do 8 maybe today? Okay. 6. I A right circular cylinder. You know what a right circular cylinder is? A cylinder, a can, right? Right circular cylinder is changing shape. The radius is decreasing at a rate of 2 inches per second. So how can we interpret that? dr dt, change in radius over time, decreasing, makes it negative 2 inches per second. Are you getting okay at least identifying the information like that? So that's half the battle, really. While its height is increasing at the rate of 5 inches per second. So change in height over time is 5 inches per second. When the radius is 4 inches and height is 6 inches, how fast is the volume changing? So when they say how fast is the volume changing, we're looking for dV dt. When, what is it? R is 4 and H is 6. What's the formula we need? They were so nice to you. Pi r squared h? And they made this one straightforward, didn't they? Okay. So, derivative, here we go. If v equals pi r squared h, and now let me mention one thing real quick. There's two variables here, yes? Which means when we do these two variables, we're going to have to think chain or product rule, right? One thing you want to look for. Do we have information to work with R and H? Or do we sometimes have to change it so that's all in terms of R or all in terms of H? In this case, they give me plug-in information for R and H, and they give us dr dt and dH dt, right? So since they've given me everything for both variables, we're going to work with it as is. There are often times, though, where they'll give you a relationship and you have to change R to be in terms of H or H to be in terms of R. Okay, so watch out for that. So, derivative of volume, dV dt. I just mentioned there is a product rule here, yes, because R is one variable, H is another variable. Derivative, how do you want to do this? I would say derivative of pi r squared. So derivative of pi r squared is 2 pi r, keep the h, and then times dr dt, because we did the derivative of that term with respect to r. Plus, now I'm going to keep pi r squared. Derivative of h is just 1, but then dH dt. Plug it all in. Again, this is a nice problem, which is good after that last problem that wasn't so nice. We know everything, guys. 2 pi, r is 4, h is 6, dr dt, negative 2, plus pi, r squared, 4 squared, times dH dt, which is 5. If I keep it in terms of pi, which is how my final answer is here, let's see. 2 times 4 is 8. 8 times 6 is 48. 48 times negative 2 is negative 96 pi. Plus 4 squared is 16. Times 5 is 80. So I have 80 pi. Negative 96 pi plus 80 pi is negative 16 pi. Change in volume over time is negative 16 pi. What would be a dV/dt label? Change in volume per time. Volume is inches cubed per second. Does that make you feel a little better? Okay. Enjoy them when they're nice like this, right? Can I get one more in? I wanted to get one more in. We can talk a little bit about it. I think I'm gonna get caught and not get all the way through it. So I'm working up my plan. Okay, an inverted cone. What's an inverted cone? Calculus likes inverted cones. Okay. Calculus likes sliding ladders, you know. There's certain things that calculus likes. And they like to hold things, inverting cones. See, this inverted cone is holding water. Actually, it's leaking water.
It's one of those nice little water cups that you eat like the office water.
Oh, yeah.
Those
The one by the water cooler?
I love it. Those are so awesome.
Okay.
I use those ones.
An inverted cone is leaking water at a rate of 1 cubic centimeter per minute. What is that?
Yes.
Not yes. What is it?
Oh.
Leaking water,
Negative.
negative. Derivative of what? It's negative 1 centimeter cubed per minute. Oh, did someone say it?
Yeah, you said volume.
Okay, I didn't hear volume. Sorry. Totally did not hear it. Okay, so dV/dt is negative 1 cubic centimeter per minute. The cone has a height of 9 centimeters and a radius. No, they couldn't give us radius, could they? A diameter of 6 centimeters, but what's that translate to? A radius of 3 centimeters. I don't really care about the diameter because what's in my formula? Radius and height. You know, I don't care about diameter. Now, this is saying these are the height and radius on the cone, which is why I went ahead and put them on here. Okay? Find the rate at which the water level is dropping when h equals 3. What did they ask me to find? When the water level is dropping, what is that? Derivative of, what'd you say? Height. Okay. So this, we're being asked to find dH dt when what? H equals 3. And, hey, what's the volume of a cone? Now, this is a situation, I kind of hinted at last time, where when we go to do this, the derivative is going to have r's and h's in it, right? But we're only given an h to plug in. We're not given an r to plug in. We're being asked to find dH dt. Do they give us any information about dr dt? We need to change this formula here. We need to get rid of r and have only h's. Now, the connection is similar right triangles. This whole triangle, you guys see the whole triangle there, yes? Radius 3, height 9. What's the water level doing? It's dropping, yes? So at some point, there is a smaller, similar right triangle wherever that water level is. Okay, and so for this smaller right triangle, I'm just going to use R and H because R and H are changing, right? They're not set in stone. You know how to make a proportion? Which way do you guys make the proportion between similar right triangles? Do you do 3 over 9 and R over H? Or do you do 3 over R and 9 over H? Or do you care? You don't care. So,
Whoa.
yep, I knew that was going to happen. The idea here is that, let's see, 3H is 9R because of cross products. What did I say I wanted to get rid of? R. So I know that H, no, I want to get rid of R. So R is, if I divide by 9, 3/9 or 1/3 H. Okay, and I know we got to go. But the idea is that's going to sub in there. Okay, I need you to start looking at homework. I know we're not done with the notes. As much as I would like to say I'm moving on just totally tomorrow, we've got to talk about a lamppost problem. We probably need to come back and finish this problem a little bit. But I can't have you guys just totally saving homework for tomorrow. You need to get in there and start thinking it through. Okay, you need to. I have to have you get in there. So, work your way through the homework. Skip certain problems, obviously. Tomorrow, we'll finish some notes. We'll talk about some homework questions. I'm also hoping to start the next lesson tomorrow, though, too. Okay? I know, a lot. We'll figure it out.
Have a good day.
Thank you. You too.